Hello and welcome. In this video, we're going to take a look at the Fourier series for a half-wave rectification of a sine wave. Now, this isn't going to be an easy process by any means, but we're going to calculate the Fourier coefficients for that sine wave by hand. And that's going to be for the complex exponential form. From there, we can take a look at what we would end up getting in a sine-cosine form, and then take a look at amplitude and phase spectra. Maybe we'll even be able to look at the power spectra too. Now, what is a half-wave rectification of a sine wave? Well, here I'm using Desmos, and you can plot this yourself if you like. Really what we're doing is we're eliminating the negative half wave of our sine wave. One way you can do that is if you just add a sine wave and an absolute value of that sine wave, all of the negative parts will cancel out. So here we have 1/2 of sine 2 pi t plus 1/2 the absolute value of sine 2 pi t. And what that's going to get us is going to get us, well, first of all, a period of 1, because you can see the 2 pi there is our fundamental frequency. But also, because of those 1/2s in there adding together, this is going to get us a maximum amplitude of 1. Right, well, now let's see about calculating the Fourier coefficients. Now here on my worksheet, you can see I've got that graph and also a little explanation about how we would get something like this half-wave rectification. If we just input some sort of sinusoidal wave and have a diode, that is going to eliminate any sort of backwards current, in which case our output is just going to be the rectified waveform that you see here. All right, well, let's start off with finding what the DC term looks like. Now, for our purposes, it's going to be a lot easier to use integration if we just define s of t as a one periodic function as a piecewise function here. And we'll just say that s of t is our typical sine wave, 2 pi t, with a period of 1, from just 0 to 1/2, and then 0 from t equals 1/2 up to 1. This is going to make it easier to integrate, because trying to integrate that 1/2 sine 2 pi t plus 1/2 absolute value sine 2 pi t is just going to be a lot more of a mess. All right, so first of all, we know what the fundamental frequency is here. Our fundamental frequency is 2 pi. But the DC term is not going to be obvious. Here for the DC term, we're trying to figure out what the average value of this function is. And it's certainly not just going to be 1/2. Probably going to be a little bit lower here because we need to have equal area above and below that line. So let's calculate C0 using the formula. Using our formula for CK, but letting k equal 0 and our period equal 1, we're just going to be finding that C0 is the integral from 0 to 1 of our signal. But since our signal is equal to 0 from 1/2 all the way up to t equals 1, we really only need to integrate from 0 to 1/2 and integrate the function sine 2 pi t. Now to integrate sine 2 pi t, we just need to do a little substitution. We can just let u, or any letter, equal 2 pi t and change the limits of integration and integrate the new function. Here, instead of using u, I'm going to choose theta to be the substitution and let theta equal 2 pi t. And doing that will result in an integral from 0 to pi of sine theta d theta over 2 pi. Now that 2 pi is just going to be a constant that we can pull out front of the integral. And from there, we'll find an antiderivative for sine theta and evaluate from 0 to pi. If we pull the negative sign out, this makes evaluating a little easier, and we just need to evaluate cosine theta from 0 to pi. And this gives us -1 minus 1. So our DC term, when we simplify this, is simply 1 over pi. And we can see if this makes much sense. We can turn back to Desmos here and plot the function f of t equals 1 over pi. And sure enough, that seems to look like the average value of our signal. Okay, now it's time to compute the Fourier coefficients for the harmonics, starting from k equals 1 going upwards. Let's take a look at that. This time we have to worry about k, so we will end up having this s of t times the exponential function of -j k 2 pi t. All right, well, once again, our signal is simply equal to 0 from t equals 1/2 to t equals 1. So we only need to integrate from 0 to 1/2 using sine 2 pi t as our signal. Once again, we'll use a nice substitution here to make this look a little tidier. In fact, we'll use the exact same substitution as before. This changes the limits of integration as well as the integrating variable to theta, and the 1 over 2 pi can be moved out front. And we have a very common form now of the form sine theta times exponential of a constant times theta. And using a table of integrals, we can see what this evaluates to be. And the table of integrals is very useful here because otherwise we'd have to use integration by parts multiple times. But of course, this is even complicated just as it is. We'll need to simplify this a little bit more. So negative jk squared is going to be equal to negative k squared. So the denominator here is simply going to be 1 minus k squared times 2 pi. And now we have to evaluate theta from 0 to pi. Let's start with plugging in pi. Well, luckily, sine of pi is equal to 0, and cosine of pi is equal to negative 1. And then when we plug in theta equals 0, once again, sine of 0 is equal to 0, and this time cosine of 0 is equal to positive 1. Luckily, when we plug 0 into the exponential function, the exponential to the power 0, that just gives us 1 as well. Now, the only thing left to simplify here a little bit is this exponential function, e to the power negative jk pi. Well, e to the negative j pi is equal to negative 1. When we raise that to the power of k, we end up with negative 1 to the k. So that leaves us in the brackets here with negative 1 to the k plus 1. And that gives us our Fourier coefficients. Now, before we say that we're all finished here, you may have noticed something about the domain here. Unfortunately, this isn't going to be defined when k equals 1. So unfortunately, this is actually just the Fourier coefficients for k greater than or equal to 2. And we're still not done. We need to calculate the Fourier coefficients when k equals 1. So let's start this whole process over again, but with k equal 1. Well, jumping ahead a couple steps here, we already know that we only have to integrate from 0 to 1/2, and we know we're going to have to make that same substitution again. Well, we can't use the same table of integrals here because we'll end up with that same problem as before. We're going to have to use a different strategy for integrating this one. And what we can use is Euler's identity. Replacing e to the negative j theta with cosine theta minus j sine theta allows us to distribute and use some other identities to evaluate the integral. By expanding through, we need to find the integral of sine theta cos theta minus j times sine squared theta. And an identity is going to help us to find the integral here. Sine theta cosine theta is equal to 1/2 sine 2 theta. And we can use a quick little substitution to find the antiderivative of sine 2 theta. As far as sine squared theta goes, we might want to take a look at the table of integrals to integrate and find the antiderivative of sine squared theta. Okay, so the antiderivative of sine 2 theta is negative cosine 2 theta over 2. So that leaves us with negative cosine 2 theta over 4 now. And then j is just a constant multiple, and the antiderivative of sine squared theta is 1/2 theta minus 1/4 sine 2 theta. Now, it might be easy to go and expand this whole thing out before we evaluate from 0 to pi. And once we've expanded it, now we can evaluate at theta equals pi and theta equals 0. Remembering that cosine of 2 pi is the same as cosine of 0, which is 1. Sine of 2 pi is the same as sine of 0, which is 0. And after evaluating, we see that negative 1 over 8 pi is canceled out, and we end up with just negative j over 4. And finally, we found all of the Fourier coefficients. We have k equals 0, k equals 1, and k is greater than or equal to 2. So if we wish to express this half-wave rectification of a sine wave as a Fourier series with exponential form, don't forget that we actually also have negative values of k, which are just simply going to give us complex conjugates. And so the DC term is 1 over pi, and whenever k is plus or minus 1, we end up with the coefficient negative j over 4. And for all other harmonics, second harmonic, third harmonic, and all of the higher harmonics, our coefficients are of the form -1 to the k plus 1 all over 2 pi times 1 minus k squared. Now, it's to be expected, since this function is neither odd nor even, that as a result, we should end up with a combination of sines and cosines. So let's see how this Fourier series translates into sine-cosine form, and then we can even go ahead and see whether or not that looks similar to the graph of our half-wave rectification of a sine wave. Now, when we translate to a different form, our DC term is going to remain 1 over pi. It's simply just a constant. It has nothing to do with oscillations. But for AK, the coefficient of our cosine terms, that is 2 times the real component of our Fourier coefficients for k greater than or equal to 1. Now, looking at when k is equal to 1, we see that we have ck is just -1/4 j, which is completely imaginary, and it has no real part. So that means that a1 is equal to 0, whereas b1 is simply -2 times -1/4. For k greater than or equal to 2, we see that the Fourier coefficients -1 to the k plus 1 all over 2 pi times 1 minus k squared is completely real. So that means that bk is equal to 0 for k greater than or equal to 2. And when we double that coefficient, we end up with the coefficient for our cosine terms. And that's going to cancel the 2 in the denominator. So we can write out our Fourier series in sine-cosine form now. We'll start with the DC term. And then for our first harmonic, the fundamental frequency, we only have a sine term, and it's going to be the only one that we end up with, and it has a coefficient of 1/2. Now, for k greater than or equal to 2, we're going to have to add up an infinite series of cosine terms with the coefficients of ak. And remember, this sum is going to start at k equals 2. All right, well, let's go back to Desmos now and see if we try to plot this, if it looks anything like our half-wave rectification of a sine wave. So here we still already have that function 1 over pi, our DC term. Let's see what happens when we add in the fundamental frequency 1/2 sine 2 pi t. And sure enough, it's starting to look a little bit closer to our proper signal. And now let's start adding in the higher harmonics. And here I've added in the second harmonic only. I have a sum from k equals 2 to 2, and you can see how close we are already. Adding in the third harmonic doesn't seem to change anything, but that is because -1 to an odd power is -1, and then adding 1, this is going to give us a coefficient of 0. So actually, we aren't going to have any odd harmonics of cosine terms. But if we start including more of the even terms, we start getting closer and closer. Watch what happens when I jump to include all the way up to the 50th harmonic. And suddenly, indistinguishable from our half-wave rectification of a sine wave. In fact, I'd probably have to zoom quite a long ways in to see any sort of deviations here. That is how close our function, our Fourier series, is to the actual rectification, simply by including the 51st harmonics. Now, if we wish to have a little bit of a condensed form of this series, what we can do is change this sum from k equals 2 to 50 to being a sum from k equals 1 to 25. But we'd have to replace all of the k's in the formula with 2k. So let's start by replacing the k's with 2k. 2k all squared would end up being 4k squared. And then we'll replace this from a sum from k equals 1 to 25. You see, it's exactly the same here. Now, this means that we end up with -1 to an even powered number all of the time, and this is just equal to 1. And 1 plus 1, well, that's just 2. And this 2 over pi we can move out front. And then our cosine term, we have 2k times 2 pi t, which could just simply be 4k pi t. And this becomes a much more condensed form of exactly the same thing. Of course, this would be actually a sum from k equals 1 to infinity, but that's a little bit hard for a computer to do. But regardless, this is a much more simplified form of writing our half-wave rectification of a sine wave in terms of just sines and cosines. Now, last but not least, let's take a look at the amplitude and phase spectra. Now it's probably best to take our Fourier coefficients ck and maybe rewrite these in terms of the even and odd values of k first. Now we see that the dc term, when k equals 0, is simply 1 over pi. No problem there. And when k is equal to plus 1 or minus 1, then we just have c1 equal to negative j over 4. But this other term, we have an alternating negative 1 to the k. If k is an even number, negative 1 to the power of some even integer is going to end up being positive 1. And we'll have 1 plus 1, which is 2 in the numerator, and that's going to cancel a 2 in the denominator. Now, when k is an odd number, negative 1 to an odd power is going to be negative 1. And in the numerator, that leaves us with negative 1 plus 1, which is 0. So all of the odd Fourier coefficients are going to be 0, except for k equals plus or minus 1. And remember again here that the Fourier coefficients for the complex form have both positive values of k and negative values of k, since we are summing all the way from negative infinity to positive infinity. But when we're translating this to amplitude and phase spectra, we really only need to look at positive values of k. K equals 0, the dc term, but then k equals 1, 2, 3, 4, 5, and etc. So now that we've broken this down into even and odd cases, then we can do the same thing with amplitude. We say that A0 is simply 1 over pi, and that has nothing to do with any oscillating terms whatsoever. That's just the dc term. And then we'll start off with A1, since it's a special case. Now remember, for AK, for k greater than or equal to 2, it is equal to 2 times the norm of the coefficient ck. Finding the norm of c1 is fairly straightforward, since it is simply of the form negative 1/4 j. It has no real component, and it only has an imaginary component. Remember that when we are looking for the norm of a complex number alpha plus beta j, that is just alpha squared plus beta squared, all square rooted. And let's look at that particular circumstance when alpha is equal to 0. Then in which case the norm of beta j is simply just the square root of beta squared, which is equal to the absolute value of beta. And if beta is equal to 0, then the norm of our complex number is just the norm of alpha. The norm of a real number is simply the absolute value. So they can kind of see where we use the same symbol for norm and absolute value. So taking the absolute value of negative 1/4 and then doubling it, we see that the amplitude A1 is 1/2. As far as even terms go, we see that all of the even harmonics have a Fourier coefficient that is completely just real. And so if we don't have both a real and an imaginary component, then the norm of a real number is simply its absolute value. We have to double that. So we have 2 times the absolute value of 1 over pi times 1 minus k squared. Now, using some properties of absolute values here, the absolute value of 1 is 1, and the absolute value of pi is pi. We have 2 over pi times the absolute value of 1 minus k squared. Now, remember, k is a number 2, 4, 6, or any even number, and 1 minus k squared is always going to be negative. So the absolute value of 1 minus k squared is simply the negation of 1 minus k squared, and that will make sure that this ends up as a positive value. If we have the absolute value of a negative number, then the absolute value simply negates it and makes it a positive number. And so this can be written in an equivalent form, k squared minus 1. And so this means that for all of our amplitude of even harmonics, the amplitude is equal to 2 over pi times k squared minus 1. And then for all of the remaining odd harmonics, 3, 5, and 7, our amplitude is equal to 0. So we can put this all together, and we can also plot the amplitude spectra along the frequency domain. You can see that when we plot the amplitude spectra, it's really dominated by the dc term and the first 2 harmonics. The amplitudes 1 over pi, 1 over 2, and 2 over 3 pi are significantly larger than any following amplitudes after that. 2 over 15 pi, and the next one after that, 2 over 35 pi, are going to be getting smaller and smaller. So we can actually get a very good approximation of the half-wave rectification of a sine wave, even just by only looking up to the second harmonic. Now let's take a look at the phase spectra. And remembering that the phase angle phi here is simply just the argument of the Fourier coefficient, or the polar angle. And that's quite helpful whenever the Fourier coefficient is either completely real or completely imaginary. If we take a look back here and we look at our imaginary and real axis, then if we have a positive real number, then our angle is 0. If we have a positive but purely imaginary value, then we have pi over 2. If we have a negative real number, our angle is pi. And if we have a negative imaginary number, then we can maybe go backwards and say our phase angle is negative pi over 2, or we can go forwards and say 3 pi over 2. So taking a look at our Fourier coefficients, our DC term, we always say has a phase angle of 0. And when k is equal to 1, we have a negative imaginary number. So that would be a phase angle of negative pi over 2. And for all of the even numbers, we've got to be a bit careful with the sign here. This is a real number, but 1 minus k squared is always going to be negative. So this is going to have a phase angle of pi. And for k equals 3, 5, 7, and all of the remaining odd numbers, well, if we just have 0 for our Fourier coefficient, then our angle is also going to be 0. And so we can plot that phase spectra, and we can see that for the DC term, of course, 0, but then all of the even harmonics are going to have a phase angle of pi. And we just have this one sort of interesting exclusive term here for the fundamental frequency, or first harmonic. Our phase angle is negative pi over 2. Now let's see, if we just plot that, just by looking at this diagram, we can really see that even only by plotting up to k equals 2, we should probably get a pretty good approximation of this signal. So we'll turn back to Desmos here, and I've already got the DC term 1 over pi. But now let's try taking a look using only cosines with magnitudes and phases if we can approximate this signal. And our first magnitude is 1 over 2 for a cosine term in the fundamental frequency 2 pi. Now we do need a phase shift of negative pi over 2. Sure enough, it's starting to look pretty similar here. Now our next harmonic, our second harmonic, has a magnitude of 2 over 3 pi. And that's a cosine term in the second harmonic, 4 pi t, and a phase shift of pi. Take a look at how close that already looks. We could go a little further if we wanted to and start including the next non-zero harmonic, which is the fourth harmonic. And that's going to be 2 over 15 pi. For the fourth harmonic, that will be 8 pi t, and that is going to have a phase shift of pi. Once again, you can see just how close it is, and we've only gone as far as the fourth harmonic. Now, from this demonstration, hopefully you have a pretty good understanding about Fourier series. We've really picked this one apart. It hasn't been an easy process. It's been a long video, but if you're still willing to stick it out for a little bit, we can even start talking about the power of each of these frequencies. So let's take a look. Now remember that the power of the kth harmonic is equal to 2 times the norm of ck squared. That's for k greater than or equal to 1. The power of the DC term is simply the norm of the DC term squared. And remember, the norm of a real number is simply its absolute value, and the norm of a purely imaginary number is also just the absolute value of beta, the number in front of j. So we'll start with the DC term. Looking back at the DC term, our first Fourier coefficient here is simply 1 over pi. The norm of that is the absolute value, which is 1 over pi, and we'll square it to get 1 over pi squared. Now, let's take a look at the sort of special case when k was equal to 1. When k equals 1, we have negative 1 over 4j. The norm of that is the absolute value of negative 1/4, which is 1/4. We'll square that to get 1/16 and double it to get 1/8. Now, for the even harmonics. Once again, we just have a real number, so the norm of that is going to be the absolute value, and then we can square it. Well, luckily, squaring that number is going to make it positive anyways, so we can just simply square that value and double it. And the remaining odd harmonics were all 0, so they will have 0 power. You can see once again, most of the power comes from just the DC term and the first 2 harmonics. Now, what about the mean square power of this signal? Well, that might be a little bit tough for us to compute, but the series is convergent, and we can get Desmos to do this calculation for us. Now the mean square power or average power of this is simply just the power of the DC term plus the power of all of the higher harmonics. Well, we do have one special case, P1. Now if we want to have a little more compact way to write the sum of only the even harmonics, we can rewrite this as a sum from 1 to infinity, but using 2k in place of k for all of our even numbers. And simplifying that a little bit, we can take our constant 2 over pi squared and move that in front of the summation, and 2k all squared will end up just being 4k squared. And this is the sum that we can try to get Desmos to evaluate. Taking a look at Desmos, I have that sum here, 1 over pi squared plus 1 over 8 plus 2 over pi squared, and then I'm just doing the sum from k equals 1 to 1 of 1 over 1 minus 4k squared squared. So this is going to be the DC term, our fundamental frequency, our first harmonic, and this is going to just be our second harmonic since we are doubling k and k is starting at 1. So this is really just the most important parts of this function. In fact, if I were to start to increase this and include higher even harmonics, that number's not going to change by very much, including the 4th harmonic, the 6th harmonic, the 8th harmonic, and why not? Let's go all the way up to the 2000th harmonic, and you can see that this number is converging. So these are partial sums. We can't really evaluate this to infinity because we'll get a nice little error. Summation bounds must be finite numbers. Well, yes, this is a very difficult sum to try to evaluate, and we only know the actual results of some of the infinite sums. So why not let's just stick with the sum from k equals 1 to 1000, which when we're doubling k is going to be the harmonics from 2 all the way up to the even harmonic 2000. And we can see that the mean square power is 0.249 repeating, which we could take to be 1/4. Going back to the worksheet then, this is 1/4. Now oftentimes we don't use mean square as being a very useful term for the average. We tend to use the root mean square, or RMS. The root mean square is the square root of the mean square of our signal. So being the square root of 1/4, that gives us 1/2. That's quite useful. We can take a look back a very, very long time ago and reminisce over how much work we've had to go through to get to this point. But taking a look back here, you see the maximum amplitude is 1. And the RMS value for this signal is half of that, 0.5. So that's a pretty useful result after all of this, that the RMS value of a half-wave rectification of a sine wave is simply half of the amplitude. And you're probably about as exhausted as I am after that video. I hope that this really tells you a lot about what you can do with Fourier constants, the Fourier expansion of a signal. And the half-wave rectification of a sine wave is kind of one of the more challenging ones. So if you're able to follow along with this, then doing a square wave or a sawtooth wave shouldn't even be quite as much work. Well, thanks for watching. I'll see you in the next video.